Today we're going to talk about a paper that was published in Medicine, Science, and Sport and Exercise entitled Biomechanical Analysis of the Sticking Region in the Bench Press. Now, the basic stated purpose of this experiment was to identify the mechanism or mechanisms that induce a sticking point in the bench press. Now, everyone that lifts heavy is aware of their sticking points. No matter whether it's in the bench, the squat, the curl, or whatever, there's just a little point within the range of motion that mechanical disadvantage and the amount of weight being lifted gang up on the muscle and muscle force generation capacity and slow down movement to glacial speeds, if not outright causing you to bail out of the lift. It's why people cheat on curls with body lean. It's why people kick their knees in the press. It's why people bounce the bar off their chest in the bench press. They know the sticking point is there, and they use a variety of strategies to maintain momentum throughout it or to defeat it. What drew my attention to this paper was a statement in the abstract that stated that the sticking point was not caused by increases in moment at the shoulder or elbow. Moment. We're generally more familiar with the term moment by a different name, torque. There are three elements of torque: the force applied, and in this case, the weight, the distance between the point of force application and the point of rotation, in this point, the shoulder, and the angle of the force vector and the lever arm, the angle of average force application. Now, intuitively, increasing the moment increases in moment should be greater at the sticking point. For the sticking point not to be related to joint angles and force of contraction and the applied resistance doesn't seem right. So let's actually look at their methods. They took 10 elite powerlifters that weighed about 93.7 kilograms, that's around 206 pounds, and those were used as subjects, and their average bench press max was 170 kilos. I think that's 375 pounds. These are pretty strong guys. The experiment called for them to do an 80% attempt, a 95% of max attempt, a 100% all-out maximum attempt, a 103% max attempt, and a 105% max attempt in the bench press. So the last two, we would assume, would be failures. Now, a good bit about this particular study was that it actually tried to make this as real life as possible with the use of competition gear and competition rules. In fact, it was full on enough that a number of the subjects actually set new PRs. Now, first thing that they did was to look at the kinetics, some of the kinematic aspects of bar movement. And if you look at this particular graphic, they use the terms acceleration phase, sticking region, then they also used maximum strength region and deceleration region, or deceleration phase, to describe what we would normally describe as driving the chest off a bar would be the acceleration phase, or driving the bar off the chest. The bar slows as it approaches parallel to the floor would be sticking point, where the bar's moving the slowest. And the bar reaccelerates after exiting the sticking point to enter the maximum strength phase. That's just simply elbow extension and humerus adduction. And then you have the deceleration phase, where the bar has to slow down voluntarily because we're slowing it to the point of lockout. We're just trying to get it locked out in the correct position. All right. So they wanted to look at the kinematic aspects of the lift and the EMG aspects of the lifter. That's interesting. What actually ended up was that they actually report 3 loads, not the 5 loads that were stated in the methods. We end up with 81%, not 80. We do end up with 100%, and we end up as 104% as the loads being reported. The 104% load is the one that's being associated as or reported as a failed repetition. Now, I'd like to be really critical here and say, well, they wanted 5 reps or 5 different loads to be reported as part of their experimental methods, but they only report 3, so we have a big failure here. But we can really live with this discrepancy since working with human subjects, athletes in particular, is a really, really finicky undertaking, and so that's okay. That's okay. They had some interesting stuff here. So if we look at the graphic here, graphic there, and we look at the 80% and the 100% and the 104% kinematic data here, you see that there was no deceleration phase in the 81% submax, and that's intuitive. That's expected because we wouldn't expect the bar to slow down with such a light weight. In the 100% load, we do see a sticking point, but then we get to the super maximal lift, and it's really hard to reconcile their data and their descriptions since it's an incomplete lift. It didn't stick, it failed. Okay? And we can sort of see an example of this with this particular graphic that shows displacement of the bar. And if you look at the 81% and the 100%, you see a fairly long range of motion. Started at, and the displacements, the start position started about 6 inches down from the AC on the chest. It's probably mid-sternum or upper sternum. And then it goes all the way up. When it finishes at the lockout, they finish almost within a centimeter or so of being directly over the AC joint. You'll note that the 104% lift wasn't a complete range of motion lift, yet the researchers treat it like it was a complete rep, to the point of assigning all 4 phases of the bar movement to measures when clearly there was the bar didn't get even past the sticking point there. Just look at that graphic. All it did was just drift north towards the shoulder. Much of what they conclude in this particular paper is then based on a comparison of a complete lift or complete lifts, 81 and 100%, to a partial range of motion, a failed lift, or an incomplete lift. Now, while we can learn some stuff from this type of comparison, we can't do that with this particular experimental design. A really, really irritating part of this paper and a problem of this paper is their reporting of body position and the sticking point. They didn't report any relevant joint angles, only some fairly non-useful data on shoulder and elbow position along the horizontal reported in rads. Okay, we can convert those into angles, but this was clearly written for an academic, not a consumption of the broad public. Now, when they did report the location of the sticking point, they reported it in units of time. That particular thing is extremely, extremely irritating. All right, so they reported it in units of time. They didn't report it in joint angles or anything else that was going to be useful to us, any useful measure that could help us in the physical description of what was going on. They did calculate some moments around the shoulder and the elbow, but there's no physical context within the paper presented to the reader that helps us evaluate the data. In fact, the variance in their three-dimensional data makes the huge variance makes any conclusions and generalization based on it and generalizing it to the exercising population really ill-advised and unwise. Now, the researchers did present and demonstrate that the sticking point lasts about 0.4 seconds. Okay? Yay. Again, this is intuitive. We know that the sticking point is there. And this is where the experiment was stated to focus on explaining why and how the sticking point occurred. But giving us data that says the sticking point begins at 0.66 seconds into the repetition tells us nothing about what's going on anatomically or physically with technique. Now, the researchers do go on to report some EMG data, and they state, interestingly, that EMG stays peaked throughout the lift. Now, where is that? There we go. This is their 100% EMG. Now, if you look at this, the most intense signal for the pectoralis was during the acceleration phase with the biggest amplitudes. It was then less active through the sticking region, and then it picked up strength of signal again in the maximum strength section. The deltoid did stay pretty active throughout the entire repetition, so if they were basing their conclusions only on the deltoid activity, it might be okay. The triceps were active in the acceleration phase, more active in the sticking region, and more active again in the maximum strength region. But this is all sort of okay stuff, but it doesn't match what they actually said. Now, what I want to do now is I want to look at a little bit of a background on how this all sort of works with a real simplification of the bench press, the EMG, and some of the levers and torque. Okay, let's first get oriented to this image. We have a bench pressing individual. This is a top-down view. The upper arm, the humerus, radius and ulna, the fist or hand. Okay, so this would be the acceleration region that and orientation, I assume, that's described in the article here. This would be the sticking region, an assumption, because they didn't describe any of the anatomical relationships here in this paper. And here would be the maximal strength region that they described. All right, so let's look at this in terms of our understanding of torque. The three elements of torque are force, distance, the distance between the force and point of rotation, and the angle of force application to the lever arm. So we've sort of simplified this to the line of the chest and the line of the upper arm or line of the humerus in each of these conditions. And we drew out this little dotted line here is the distance between the end of, or excuse me, the force application, the resistance, that's where the weight is supported, and the point of rotation. And the same thing here in the sticking point region, we have a longer distance between the actual force generation and the actual resistance. and that gets smaller as we go up past the sticking point. All right. So at the beginning phase of this, we have the acceleration phase, where we're going to have muscles kicking in very quickly. Now let's basically sort of scope this out here. So basically, we have the pectoralis major and minor basically biting into the upper part of the humerus here. We also have the deltoid basically reaching around from the clavicle or the scapula in the back to the clavicle up front and down to the deltoid tuberosity on the humerus. Okay, those two muscles are active in the bench press, as well as the triceps brachii on the posterior portion of the humerus. They also, in this paper, looked at the biceps also, although the bicep really isn't involved in the bench press too much other than a stabilizer. All right, so we have the muscles in play, we have the bones in play, the joints in play, and we know that the distance between the force application and the point of rotation is small, gets bigger. This means that it's easier to move this arm from here to here in this direction than it is to keep moving it from here up. Because the distance between these 2 points is farther than the distance between these 2 points. And as we move this humerus up in this region, it becomes progressively easier to move the weight. That's why you can do bigger weights with partials. All right, so the angle of force application is also an issue here. Now, if we're looking at the pectoralis muscle here, it's basically having to pull around in this direction. Let me make that a little bit darker. All right, so it has an angle of pull that has a vector sort of in that direction. Now, when we get over here, we have the maximum distance away from the rotation, and we have the resistance pushing down directly at 90 degrees of this force application. The force application here is vertical, is essentially on the horizontal. Just think about it. The pectoralis is laying right here, and it's trying to pull this straight this way. So it's sort of a difficult angle. It's just got a little tiny little hoop around here. So we're in a disadvantageous position here and a disadvantageous position here. Then as we move further up the chain and we get into the maximum strength region that the individuals talked about, we are getting to a much more muscular advantageous position. All right, so if we look at this, in this little bit right here, we're trying to overcome inertia. So if we're trying to overcome inertia, all the muscles are going to be activated in order to get some acceleration going. And that's exactly what occurred. Now, so we have the pectorals, we have the deltoids, we have the triceps, and the authors contend that there were some biceps involved in this acceleration phase, although their data doesn't seem to show it on the EMG. Now, at this point, we have a disadvantageous position. The pectorals are having a very difficult time pulling anything in here. So what has to happen is the triceps have to kick in and cause a elbow extension. And this sort of falls into line with what they actually did show in their EMGs. And then as we move past the sticking region, we have both the pecs and the triceps kicking in simultaneously. And that's actually what we saw in the EMG. So it's real easy to understand how EMG should be phasic and in terms of doing a complete range of motion exercise. The issue that they have is that the EMG was stated to be at maximal activity throughout, meaning that there was no variation between the the acceleration phase, the sticking region, and the maximal strength area. That's not what we saw. So their AMG actually shows what you would expect, and it's worrisome that they concluded that the signals stayed consistent. And if you actually look at this EMG right here, look at the 81%, the 100%, and the 104%, you'll notice that in none of them did EMG magnitude and durations of signals stay the same. There is considerable variation. If they actually have that data that showed that EMG activity stayed constant, they certainly didn't show it here. What is presented visually and in numbers, the limited numbers they did show, does not match the text, where they actually say that the prime mover muscles for the 100% and failed loads achieved maximal activation levels at the commencement of ascent and maintained this essentially unchanged throughout the upward movement of the bar. So there's no numeric or visual data representing the complete EMG data set for us to assess, only the interpretation presented by the authors. So we don't have information to go by in order to actually validate what they actually say. Probably the best piece of data in this entire paper is the trajectory graphic, as it describes the effect of load on bar trajectory. The heavier the weight, the more closely we carry it towards the shoulder at the end of the movement. So, did the researchers accomplish their purpose to identify the mechanism or mechanisms that induce a sticking point in the bench press? Not even close.